Hello, this is Jack Jackson. In this video, we're going to give an overview of some of the accomplishments of the medieval Islamic mathematicians. So first of all, the period that we're talking about, time-wise, is from mid or late 8th century to the early 14th century. So several centuries that we're talking about. This is called Islamic mathematics because the common denominator is that this happened in countries that were ruled by Islamic leaders. Now, this had a variety of different nationalities and ethnicities. You had Arabs, Persians, North Africans. You had the Moors in Spain. There were people here over a large area, going from the Atlantic and Spain and all across northern Africa into uh, most of what's now Turkey, all the way over, really all the way over to India, and at certain times even all the way almost to China in times, and pretty much all of the Arabian Peninsula. So there's a large geographic area that we're talking about. From at certain points, you did have leaders over the entire empire, but at other times you had more localized leaders, uh, and they were not all uh, is Muslims either. Some were Jews, some Christians, mostly Muslims though, that led the way here. During most of this time, it's often considered European Dark Ages, and sort of a Eurocentric view of things is that you had the you had the Greeks, and then you had this period of several hundred years where not much was going on in Europe, and then you had the Renaissance when things picked up, and that's a very uh, narrow view of things. In fact, there was a lull in mathematical uh, growth in Europe, but meanwhile, the Islamic mathematicians were having a renaissance during this period that we're talking about. And they preserved and translated and transmitted ancient knowledge of the Babylonians, Egyptians, Indians, and Greeks, and they developed the Hindu Arabic numeration and arithmetic. And this transmission to Europe began in about the 12th century. So again, European mathematics historians from years ago limited their acknowledgement of Islamic mathematics to really these two main ideas. But that's not all that was going on. There was a lot of really important original work as well. Um, One of the things is you had assimilation and expansion of mathematical ideas from these ancient cultures. So not only did you have preservation of, say, Greek mathematics, but extension of that. And it was combined with knowledge from the Indians and Egyptians and Babylonians together to create a new and a more advanced system as this combined mathematical ideas were going forward. As with a lot of mathematics, a lot of what they did was focused on solutions to practical problems. Some of the areas they were interested in are calendar making, timekeeping, geography, inheritance calculations, astronomy, and other areas. But one of the tools that they ended up creating was algebra. So the Islamic mathematicians really are responsible for creating the area of mathematics known as algebra, a very, very important area of mathematics. They did proofs based on geometry, but with techniques that moved away from geometry, so that ultimately the algebraic techniques sort of stood on their own without reference to the geometry that was going on. Nevertheless, they did their proofs more in the classical Greek style. So you can see some obvious influences, say, of the Greeks and their insistence on proof, and also on their geometric approach to things, but also the influence of, say, the Babylonians with their computational abilities all thrown in together. They did some work in number theory, geometry, trigonometry, and astronomy. You saw advances in all of these areas. So early on, there were three numeration systems that they had. First of all, there was a finger counting system that the merchants used, and they had sort of a way of using their fingers to do not only just counting, but do basic arithmetic like adding, subtracting, multiplying, dividing, that sort of thing, but using their fingers to represent the numbers. And so that was a sort of the business class of folks took care of that and used that system. They also had the holdover from the Babylonians of this sexagesimal system, the base 60 system, but instead of using Babylonian numerals, they use Arabic letters for the symbols for the different things. But there was this idea of grouping things in 60s. It was very popular in astronomy. Even if you go back to some of the Greeks, like Ptolemy, for example, when he was doing his work with astronomy, he was using base 60 numerals, whereas he was using actually the Babylonian system instead of using the more what would have been normal for him, the Greek number system, which he may have used for other things. So, and in fact, we have vestiges of this sexagesimal system that still are with us today when we talk about degrees, minutes, and seconds. 60 seconds is a minute, 60 minutes is a degree. And so if we're doing things measuring with angles, which arose in geometry, trigonometry, astronomy, those things we still often use that sexagesimal thing, also in terms of telling time, which is also related to astronomy. When you have 60 seconds is a minute, 60 minutes is an hour. So we still have these ancient Babylonian ideas still through today, and of course that ran through the Arabic system as well, and the Islamic mathematicians there. And then ultimately they had Indian numerals, which came from India, which they sort of standardized the symbols for them and added to the ability to calculate with them. Hence, they're known today as Hindu Arabic numerals. In fact, the Europeans actually just called them Arabic numerals, not realizing that they actually came from India, and perhaps even maybe even started some of the concepts even in China, as we discussed in an earlier video. There were some scholars that actually had some works that explained all three systems side by side and explained what was going on with these systems. However, ultimately, the Hindu-Arabic numeration system won out, and is the one that we, of course, still use today. Al-Khwarizmi, who lived from 780 to 850, gave detailed explanations how to compute with Hindu-Arabic numerals, including how to add, subtract, multiply, divide, find square roots, and he used algorithms that were done on a dust board that you could sort of erase, sort of think like a chalkboard or whiteboard that we might have today, where you could write on there and then erase certain things and put things back. And so the algorithms that he used involved, erasing things and replacing them with other things. First of all, let me apologize right up front for mispronouncing these names. I'm not sure how to pronounce all these Arabic names, but so I guess this is Al-Qudsi. Modified the algorithms to be written on paper. That was around a paper he wrote around 952. He included decimal arithmetic in his calculations. Al-Samawal in 1172 gave decimal approximations to repeating decimals and irrationals. And Al-Kashi in the 15th century made full use of the decimal system. So you could say by that time, for sure, the modern numeration system was in full use and full value by that time. But a lot of it was in place at least by the time of Al-Khwarizmi. Al-Khwarizmi also in 825 wrote a book called, translates as The Condensed Book on the Calculation of Algebra and Al-Muqallaba. Okay, and those two terms that ended up not being translated from the Arabic basically mean restoring and comparing. and they refer to two operations you do with um, equations. Basically, restoring is this idea of taking a term from one side and moving it to the other side, essentially by adding its opposite to both sides. But basically, this balancing out equations by moving something from one to the other. And comparing is basically adding the same amount to both sides. Very similar concepts. But those were the techniques that he used to working with equations. And so notice that algebra becomes, or algebra, however it's pronounced, became our modern word of algebra as it was moved into Europe. So Al-Khwarizmi probably deserves the title father of algebra. If you remember, we also have seen that term applied to Diophontus, but personally I think it's probably more appropriate to call maybe Diophontus the father of number theory and Al-Khwarizmi the father of algebra. But he certainly wrote the first algebra textbook, which is this book from 825 that we were talking about. The algebra at this time and for some centuries to come was presented in words and processes focused on finding numbers, which were not necessarily links, even though the results were proved geometrically. So first of all, let's talk about the words. So instead of using symbols that we have for x for a variable, for example, and superscripts for powers or exponents, and so forth. In fact, even our modern symbols of abstract, multiply, divide, and even the equals are much later on. So a lot of this was presented in terms of an equation might be expressed completely in words and then was worked with there. But one of the things that they did, Al-Khwarizmi did here, is he also started looking at numbers and not necessarily thinking them as links. And even though they were proved geometrically, he did the proofs by using Euclidean geometry methods and the style of the Greeks. But at this point, the algebra is actually designed to be something that could be done without having to draw the figures out. And he came up with more modern kinds of techniques, even though the modern symbolism was not actually used yet. So the Greek approach was important in justification, but the emphasis in execution was removed from geometry, what we would now call an algebraic emphasis. Among other things, he did solutions of quadratic equations, but he only wanted positive coefficients and positive solutions. So rather than having one general form of equation, he had multiple forms, I think at least 6 different forms, depending on manipulating it so that he made sure that the coefficients were positive. For example, ax squared plus b equals 0 was a different form than ax squared equals b. Right? We would probably consider those more or less the same form, but you had to write it in terms of so that all the coefficients were positive as well as the solutions. Here are some other important algebraists: Ibn Turn, Thabat ibn Qurra, Abu Kamil, Al-Karaji, and Al-Samawal all made important advances in algebra, and we had a gradual move away from geometric interpretations. Ultimately, they did polynomial algebra, sums of series, induction. Khayyam and Al-Susi worked with solutions to certain types of cubic equations. And again, no symbols, everything was done just in words. And notice I'm not specifying too much about which results and things were due to which specific mathematicians here. I'm kind of lumping all of the Islamic mathematicians in together over many centuries. Combinatorics and number theory is another area that they made advances. Combinations and permutations were used in counting. Pascal's triangle was examined, again, many centuries before Pascal, but quite a bit later than the Chinese were using Pascal's triangle. Induction proofs were actually used then. There's actually some work in number theory. An example is perfect numbers. Perfect number is a natural number which is the sum of its proper divisors. And Euclid knew about those. There's some material in the Elements where he talks about perfect numbers and shows a way to find some. So the Islamic mathematicians had an extension of that, or a variation on that, where they took a pair of natural numbers, each of which is the sum of the proper divisors of the other. So you had an amicable number pair. Al-Farisi in the 12th century found a general method for finding amicable number pairs. Eventually, they were working toward this idea of a real number, which is a linear correspondence between the numbers and the points on a line. And this removes some of the Greek distinctions between cubes, squares, units, and rational and incommensurable numbers. So if you remember, the Greeks had a different theory for rational numbers and irrational numbers and didn't think of those as, sort of comparable. They're sort of two different things. So the Islamic mathematicians are starting to blur the lines there and starting to think of both of these as just numbers, which is more of our modern approach. Also, the Greeks, since they were thinking geometrically, considered cubes, squares, and units completely different kinds of things, right? A unit would be, maybe a length along just a distance, right? Whereas a square would represent an area, and a cube, of course, would represent a volume. It doesn't make sense to say add a volume to a constant times a area plus add a length. That doesn't really make a lot of sense geometrically of what's going on there. But the Islamic mathematicians start to see no problem with that because they said, well, whether it's a cube, a square, or a unit, it's still a number, and we can operate it with that way. In geometry, they did some constructions. Some were practical, some were more theoretical. So this is adding to the types of constructions that the Greeks already had. And they even used algebra to find some geometric constructions. They found volumes by the method of exhaustion, and they actually did some work on parallel postulate, trying to prove it, which turned out to be, of course, impossible. But the work that they did there actually was leading toward non-Euclidean geometry, and that predates by a few centuries the later work by some Europeans who eventually were able to actually find some non-Euclidean geometries. In trigonometry and astronomy, first of all, trigonometry and astronomy were considered exactly the same field. Trigonometry was a tool for doing astronomy, and the need to do astronomy drove the need to make techniques for working with trigonometry. So they gave the 6 basic trig functions, more or less as we have them today, and the sine replaced the chord as the basic trigonometric function. So the chord was the basic trig function, say, that was used by Ptolemy, for example, and the sine is a function that was used in India. So it's pretty clear that they probably took some of this information from India, particularly some of the astronomy that they learned from India and from Mesopotamia, and put that together, including some of their use of trigonometry. They developed some trigonometric tables. In addition to plain trigonometry, they did some spherical trigonometry. And again, trigonometry was used in astronomy, and ultimately, though, they were able to lift trigonometry out of astronomy and start thinking of it in its own right. So you had a remarkable period of time over these centuries from about the 8th to the 14th century whenever Islamic mathematics became dominant. Remember, this start of this follows a period of expanse and where the Islamic leaders became military leaders, and political leaders, as well as religious leaders, and going out and conquering a big chunk of the world that they knew at that time. After that kind of settled down, and then they went to actually ruling that, there were at least a few of those leaders who really wanted to uh, promote knowledge, and so they set up institutions like the House of Wisdom in Baghdad, that they were able to uh, attract scholars, support that, and it became actually a religious imperative to seek out advances in science and mathematics and other areas of secular thought, as well as, of course, continuing to expound upon their religious thought as well. So notice that in this case, it's not a conflict between religion and science. It's actually religion helping science along and science helping religion. And so they were both seen as ways of revealing knowledge through their holy scriptures and visions, but also through scientific development as well. So science and religion went hand in hand. But then after this, you know, later in the 14th century and a little bit after this, we have another turn of events where now uh, the Islamic folks who were in charge became much more fundamentalist. And once you get a fundamentalist religion, that uh, they have start to have this idea that their religion has all of the ideas that are correct and all the ideas that they actually need, then any other knowledge, especially if it comes from other sources outside their religion, but even if it comes from within, if they think it's not from from their religion, then what happens is they think that it's either uh, at best irrelevant and at worst dangerous, and so that gets suppressed, and things happen like burning books and so forth. At the very least, what happens is there's no longer support for developing ideas. And if you really want to develop ideas, there has to be a class of folks that can devote their time to thinking and developing knowledge, right? And they need to be supported in that, like at Alexandria in the library and museum there, or in the House of Wisdom in Baghdad, where you had a ruler supporting that. Once that support is gone, then it can no longer attract all the best and brightest. And eventually, if you get to the point where the religion becomes so fundamentalist that it completely suppresses knowledge, then you have an even bigger problem. And and you have a big disconnect between then science and religion become adversaries, or not just science, but any knowledge outside of the religious sphere becomes a problem. And different religions have had that. It's not unique to Islam. The Christians did that in Europe. We've already talked about how rulers took over in China and suppressed other knowledge by burning books. This is a thing that happens a lot from time to time in culture to culture. So when you get a chance where folks encourage diversity of thought, where they support learning, and even when their religion even makes that imperative, religion and science go together and they both flourish. And when you get, for whatever reason, and you close your mind off to other ideas, then things wither and go backwards. But from the 8th century to the 14th century, Islamic mathematicians were the best in the world. They not only preserved the ancient knowledge of the Babylonians, Egyptians, Indians, and the Greeks, they built upon that and created some great new areas of mathematics, especially in including algebra.